Hello, everyone. My name is Scott Haskell, and today I'm presenting on shockwave evolutions during histotripsy treatment in ex vivo tissues. For therapeutic applications, a number of cavitation monitoring techniques, such as diagnostic B-mode ultrasound imaging and passive acoustic mapping, have been developed to observe the magnitude of induced cavitation. However, these techniques have limited ability to resolve the cavitation dynamics or a level of damage generated with the materials by cavitation, which is essential for monitoring treatment progress in cavitation-based ablation therapies such as histotripsy. Acoustic cavitation emission signals, or ACE signals, in the form of cavitation-emitted shockwaves, are an appealing candidate for non-invasively quantifying cavitation-induced material damage. As viscoelastic materials, such as tissues, are repeatedly exposed to cavitation, they are incrementally liquefied by it. The material properties of the nucleation medium are known to affect the cavitation dynamics, which in turn are known to affect the cavitation shockwaves emissions. Features of the ACE signals can thus be expected to change as a material is repeatedly exposed to cavitation, a result of the evolving material properties of the medium. By monitoring these patterns, models to predict damage outcomes based on measurement of the ACE signals can be developed. Recent studies in hydrogels have found that cavitation collapse times and amplitudes increased monotonically with a number of histotripsy pulses applied, which agreed closely with image bubble lifespans. These trends were seen to be consistent across gels, but evolved at different rates depending on gel stiffness. They also observed that nucleation, collapse, and rebound shockwaves measured from the broadband hydrophone and the narrowband receive system of the histotripsy array demonstrated similar trends in timings and amplitudes. In anticipation of translating this technique to in vivo applications, it must first be verified that the trends observed in various hydrogels are consistent with those observed in tissue. Therefore, cavitation was generated in ex vivo bovine liver and brain samples, and ACE signals were recorded via the receive system of the histotripsy array. Following cavitation exposure, each of the tissue samples were fixed in formalin, hematoxylin eosin stained, and quantified for induced damage. It was observed that bubble lifespans increased with acoustic dose in both liver and brain samples. Collapse shockwave amplitude also increased with dose in the brain samples. However, collapse shockwave amplitudes in the liver samples decreased quickly during the first exposures, plateaued, and then increased again towards the later exposures. Histological damage was evaluated as the percentage of the treatment area with visible cell disruption. Damage fraction increased with acoustic dose in both liver and brain. Bubble lifespans and histology damage correlated, but collapse shockwave amplitude and damage did not. In this study, it was observed that features from cavitation events generated in ex vivo tissues demonstrated trends that were dependent on cavitation exposure and were consistent with the findings identified from experiments in hydrogels. Pulse-to-pulse variabilities in ACE feature measurements interfered with accurate comparisons to histological damage evaluations. To resolve this issue, a moving window average filter was applied to the lifespan and shockwave amplitude data, which improved the correlation between them and the histology damage data. Measured ACE features, or combinations of them, could be used to extract the amount of cavitation-induced damage for applications of treatment monitoring and dosing. And with that, that finishes up my presentation. I'd like to thank the rest of the members of the lab as well as the funding for this project. Thank you very much for listening.